Experience the future of collaborative 3D design and extended reality, powered by the Horse Project. Horse supports HoloLight, an extended reality software company, by enabling secure remote rendering for XR collaborative sessions. HoloLight offers HoloLight Space, an XR engineering application designed for visualizing, interacting, and collaborating on original 3D CAD data in AR and VR. HoloLight Space is powered by HoloLight Stream, a proprietary XR streaming technology that offloads rendering processes to local servers or the cloud, allowing for high-fidelity XR experiences on a variety of devices. We are now witnessing a multi-user XR session in HoloLight Space. The scenario involves two users from different locations, represented by avatars, collaborating in a shared virtual environment. They can interact with 3D objects and communicate with one another in co-design in real time. This use case requires high bandwidth and low latency. When this solution is scaled and used to share classified data, the session is vulnerable to cyber attacks. Such a session can be disrupted by avatar jitter, communication delays, and poor user experience.
In case of an individual user during an XR experience using the streaming technology, the streaming is susceptible to network attacks. This workflow of the Horse Project is defined for real-time threat detection and mitigation within the operational environment. The workflow initiates with telemetry acquisition from the underlying infrastructure. The SM module ingests measurements from both infrastructure components and domain orchestrators, forwarding them to the pre-processing module, which performs data normalization and schema alignment to produce a unified data representation. The normalized data is then streamed to the DEME, where continuously running detection pipelines based on rule-driven analytics, statistical models, and ML-based classifiers identify potential threats and attack patterns. In parallel, the processed data is passed through the PAG component for anonymization and policy-compliant handling before being stored in the SM's Elasticsearch. This repository provides feedback data for periodic retraining and refinement of the ML models used across Horse components. Upon detection of an attack or anomaly, DEME issues a notification to the DTE, which synthesizes the event into a high-level mitigation intent expressed in a machine-readable format. The intent is forwarded to the IBI component, which queries the CKB to retrieve appropriate mitigation strategies. The IBI then generates a concrete operational lifecycle describing the sequence of mitigation steps required to address the detected threat. This lifecycle undergoes compliance validation by the CAS component to ensure alignment with Horse policies and external regulatory frameworks. Once validated, the lifecycle is transferred to the RTR component, which derives the final set of actionable mitigation instructions to be deployed in the infrastructure. These actions are sent to the EPEM to verify consistency with the available infrastructure state. The DOC executes the necessary orchestration mechanisms and deploy the required security controls or configuration changes across the target network segments, thereby executing the mitigation procedures triggered by this workflow.
In this use case, we also validate the prediction workflow. The early modeling provides the emulated environment with all the structural and behavioral models it requires, describing potential threats and attacks, their expected impact on the 6G system, and the projected impacts of enforcing mitigation or preventive actions. The predictive threat analysis happens within the network digital twin environment, which starts with the telemetry ingestion from the operational infrastructure, which is forwarded to the prediction and prevention NDT. This component processes the collected data to predict the likelihood of upcoming threats or attacks. When it predicts a potential threat above a defined confidence threshold, it triggers the DTE, which synthesizes the event into a high-level preventive intent and submits it to the IBI. Upon receiving the intent, the IBI queries the CKB to retrieve the corresponding preventive strategies and enforcement primitives. As in the detection workflow, the IBI constructs an operational life cycle describing the full sequence of proactive actions required to mitigate the predicted threat. However, given the inherent uncertainty of predictive analytics, this life cycle undergoes an additional validation phase executed within the sandboxing environment. Specifically, the life cycle is passed to the sandboxing module, where the impact analysis NDT emulates the execution of the proposed preventive actions to assess their expected impact. The impact analysis NDT returns quantitative impact metrics to the IBI, which evaluates them against predefined admissibility policies. If the predicted impact falls within acceptable thresholds, the life cycle is forwarded to the CAS component to verify alignment with horse policies and the applicable regulatory framework. Upon successful validation, the IBI submits the approved life cycle to the RTR module, which derives the final set of executable preventive actions. These actions are then handed to the DOC component, which executes the necessary orchestration mechanisms across the infrastructure, thereby proactively reacting to the predicted threat.
In the CNIT testbed, this workflow is validated through the XR streaming use case, where the HoloLight Space Server and the HoloLight Space Client are at two nodes of the 5G network.
With the involvement of HORSE, HoloLight is able to run multi-user sessions with smooth user experience and secure data streaming. The users are able to work together on a CAD model and interact with each other. With HORSE, HoloLight sees great potential in scaling up the technology securely.